Okay, so this is our assignment week 8 problems. So let us start discussing. Uh, the eigenvalue of the Hamiltonian operator h cap equal to sigma dot v vector will be whatever which of these four options. So we first write down the Hamiltonian and try to simplify if it is possible to simplify the Hamiltonian form and then see what will be the eigenvalue. So h cap equal to given the Pauli matrix spin matrix sigma vector dot magnetic field b vector. Now your magnetic field can have particular direction, right? So it can be modulus of magnetic field into the direction signified by the unit vector n cap. So here you can replace that sigma vector dot n cap. This is the modulus of b, which is actually your Hamiltonian. Then what will be your Hamiltonian square? So a square will be sigma dot n cap square dot mod b squared. So here there can be a simplified expression that sigma dot n cap square, if you derive, that will be equal to your identity matrix. So that is equal to I times this mod b square. So actually you are getting h square equal to and identity matrix times mod b square. So identity matrix, you know, that is just 1001, right? So this is just a constant, so I am taking it to the front. So this is not some matrix reversal, so that is it will not matter whether you write it here or before, but actually the final thing will be mod square 0 0 v mod square is the final form of the Hamiltonian matrix squared. Now, for such kind of a matrix, you know that if the matrix is represented as a diagonal matrix, then the diagonal elements are its eigenvalues, right? So, basically it means that H square matrix has so sorry, the actual meaning should be that if a matrix is diagonally written, um, yeah, then the diagonal matrix should be its eigenvalue. So H square matrix you can also check it from here, that if this is your matrix, then how do you know what is your eigenvalue? So basically you do that matrix, you want to know the eigenvalue of minus lambda I equal to 0, where lambda is your, so I am for here because your eigenvalue is um, of the h square matrix. So lambda I am taking as the eigenvalue of the h square matrix. So you have to write h square minus lambda identity matrix equal to 0. That means b mod square minus lambda 0, b mod square minus lambda, and this whole thing's determinant will be equal to 0. That means you have b mod square minus lambda whole square minus 0 equal to 0. So basically b mod square minus lambda equal to 0, or you have lambda is equal to b square. That means you have the eigenvalue of this matrix as mod b square. Now if that is the case, then the Hamiltonian actually, which is not the square Hamiltonian but the real Hamiltonian matrix, will have mm, eigenvalue square root of mod b squared, which is equal to plus minus mod b, because if the square matrix has a some eigenvalue, then the actual matrix will have that eigenvalue square root. So here there will be a minus plus sign involved. So you are getting plus minus mod b is your Hamiltonian matrix's eigenvalue. So this is your final answer, that your eigenvalue for the Hamiltonian matrix will be plus minus mod b. Okay, now you can also ask that how am I writing that sigma dot n cap whole square is an identity matrix. So this is something that is coming later on also in different assignment problems, but for here I'll show it once, that sigma dot n cap square, how that is identity matrix. So it is basically that sigma dot n cap whole square. So basically you have the power spin matrix and unit vector direction, right? Now this is equal to sigma dot n cap whole squared. So this you can write down as sum over I sigma I ni and sum over j sigma j nj. So this is because they are written as squared, so you can take, like, you can write them down like this with two different indices I and j. So you sum them, you bunch them together, so it is summation over ij sigma I sigma j ni nj, where ni nj are the components of the unit vector n cap. So you know that Pauli spin matrices have some particular properties, like there is a product property, what is sigma I sigma j spin product, so that is equal to delta ij times an identity matrix plus epsilon ijk, its value becomes plus 1 if ijk are in cyclic order and minus 1 if they are not in cyclic order. So epsilon ijk and sigma k. So this is a property of Pauli spin matrices which you can use here. So this is equal to ij and you multiply it by the remaining term, which is ni nj plus epsilon ijk sigma k ni nj. So the first term is just delta ij ni nj times the identity matrix I plus sum over ij plus ijk ni nj sigma k. Now because this is a Kronecker delta sign, so you know the delta ij is Kronecker delta, which is 1 if I equal to j and equal to 0 if I not equal to j. That means this first term will only be non-zero if I equal to j. So you suppress one summation, two summation to a single summation of I, and because you have to set to have this term non-zero, you have to set I equal to j. That means you are getting, instead of ni and j, you will be having ni squared times identity matrix I plus, you see here this will be an interesting case, that you have one hand you have ij in I in j, okay, and on the other hand you have epsilon ijk sigma k. Now when you write down or solve this summation, for simplicity sake, if you look at this term, so this is symmetric by the interchange of I to j. That means whether you write ni nj or you write nj ni, because this is just a product of two components of the unit vector, these are not matrix, so this, whether you revert the order, it does not matter, it does not change the meaning. So it is symmetric by the interchanging of the indices I and j, but over here this term, this is asymmetric by the interchange of I to j because you see that here epsilon ijk will be equal to plus 1, but if you take epsilon jik, it will be minus 1, right? So by that you know that the second term only, if you try to write it down in a summation form, then let's say ij is, let's say for simplicity, and also this epsilon ijk equal to 0 if any three of the terms are equal, if I equal to j, or j equal to k, or I equal to k, or all of them are equal. So any case of equality, then epsilon ijk is 0. So that term again anyway you cannot consider. So for simplicity, to check whether we are getting a correct sum or not, let us take I equal to 1, j equal to 2, and k equal to 1 only, let's say. Then what will be the summation? So this is summation over I and j is 1 and 2, n1 into epsilon, sorry, you have to set k equal to 3, because other than that this thing will give you 0. So this is epsilon 1 to 3 sigma 3. Now because you have the summation over 1 and 2 taken, so like that you can also write another term. So out of this summation, uh, so like you have this summation over 1 and 2, right? So out of this summation, like you write this term, you can also write the other term which is n2 n1 and epsilon 213 sigma 3. So basically here I equal to 1, j equal to 2, and here I equal to 2, j equal to 1. Both are possible under the summation. So in one case you have epsilon in one into epsilon 1 to 3 is plus 1 into sigma 3, and on the second case you have into n1 epsilon 213 is minus 1, because the cyclic order has changed, so this is minus sigma 3. So you have plus n1 into sigma 3 minus into n1 is same as n1 into, so minus n1 into sigma 3, which is 0. So this term is giving you 0, that you can see, because one part is symmetric and the other part is asymmetric. So only part you are left with is this term, which is non-zero. But also you know that because these are so ni square summation, this will be equal to 1. Why? Because n is a unit vector. So very easily n cap magnitude will be equal to 1. So if n cap you write as ni I cap summation over I, then the sum over these terms ni squared, which is basically the magnitude of this n cap vector, which is the unit vector, will be equal to 1. So this is nothing but 1 times the identity matrix plus the second term is coming as 0 that we just saw. So this is just I. So from here you can say that definitely your this term is just equal to the identity matrix. So this is how you simplify your terms. For first write down the Hamiltonian squared matrix, and once you know its eigenvalues, it is easier to get the square root and get the eigenvalues of Hamiltonian or H cap. So by that you have solved this first problem, that plus b and minus b with a modular sign is the answer. So C is the correct answer. Now question number 2 is also a similar question, where it is asked that the Hamiltonian is again sigma dot n cap, but there is this additional epsilon term. So this is almost similar to this previous term, as you can see. Here epsilon is a constant having the dimension of energy, and n cap is arbitrary unit vector. Sigma are the Pauli spin matrices. Then the energy eigenvalues of the Hamiltonian will be what? So you can see the similarity of this problem with problem number 1. So we'll show it here only, because it is already solved in the problem number 1. So the only structural difference is that here h cap is epsilon sigma dot n. So here they have given you the unit vector formation, and in the question number 1 we have to represent in the unit vector from this field present. So how? Because we took sigma vector uh, dot sorry we took mod B as a magnitude of B common, and then the direction of B as an n cap vector, and taken a dot product with sigma spin matrix. So similar thing here is done, is epsilon sigma dot n cap. So here you had B mod and here you have epsilon, and rest of the things are just the same format of the structure of H. So from the same procedure how you solve question number 1, you can also solve question number 2. That I am not going to show you because it is exactly the same, but the eigenvalues will be again, instead of plus minus mod B, you have plus minus mod epsilon, or because epsilon is a energy, so we take that it is positive. We assume that it is positive, so that is why in the option there is no modular sign given. So the actual answer will be plus minus E. So plus minus E, or sorry, plus minus epsilon is the correct answer. Now question number 3 is, if a system is in the state epsilon psi theta phi equal to all this linear combination of y1 minus 1, y1 0 and y1 1 theta phi, and mz is measured, then the probabilities of getting the measured values with m equal to 1 will be what? So here you can see that your epsilon theta phi is written down. We can also solve it here because this will be a short problem to solve. So here epsilon theta phi is written down in the these sorts of terms, which are nothing but the y lm theta phi kind of terms. So this is y lm theta phi. This is a linear combination of that. Linear combination y lm theta phi, these are the eigen basis that psi lm is written down in, and lm is basically changing for different three of these different terms. Like for the first term, l equal to 1, m equal to minus 1, l equal to 1, m equal to 0, and here l equal to 1, m equal to 1. But you have been asked that for m equal to 1 you have to measure the probability. So out of these three terms, m equal to 1 is only possible for the term y1 comma 1. For the rest of the terms, m is 0 or minus 1. So for all three terms, l is fixed at 1, so m value can be minus l to plus l in a gap of 1. So this is minus 1, 0, plus 1. Three values are possible. Out of these three, y1 comma 1 has m equal to 1 value, and the coefficient factor for this term is coefficient is equal to minus root over 2 by root over 7. Now you know that if psi can be written as simplified sum over n cn phi n x, then psi x is like written down as a linear combination of the eigen basis vector phi n x, so sum over n. Then the coefficient term cn is actually the with each of this phi n. So the probability of the state being found in any of these phi n state is Pn is equal to basically a linear product of phi n with psi. That will be nothing but Cn whole mod square. So this coefficient whole mod square is the probability of the state being found in the state phi n. So similarly, the probability of the state psi theta phi to be found in the state y11 theta phi is simply this coefficient whole mod square. So minus root 2 by 7 root this coefficient whole mod square, which is just 2 by 7. So 2 by 7 is your answer, number C. This is the correct answer. Now question number 4, the number state 0 is the ground state of the harmonic oscillator, which is annihilated by a cap equal to root over this operator is annihilation operator form given for this harmonic oscillator problem, and 0 is the ground state given. Then the position space wave function psi naught x will be what form? So let us solve it by going down here. So question number 4. You have a cap psi naught x equal to 0. Why? Because psi naught x is the ground state below which no state can exist. Ground state is a minimum energy state, and a cap is the annihilation operator. So the basic idea is that if you operate the annihilation operator on a state, you actually go down one state below, simply saying. But because below ground state there is no state physically possible, so when you operate the annihilation operator on the ground state, you end up with 0 on the right hand side. Now once you know this relation, you put down the form given of the annihilation operator in the question, which is 1 by root over of b or beta, uh, then x cap plus I, which is the imaginary I, beta squared by 2h cut p cap psi naught x equal to 0, which is uh, so 1 by root over beta you can ignore because that can be like compromised, like adjusted with 0. But x cap acting on psi naught x is basically x times psi naught x, because you get back the position operator, you get back eigenvalue as the position, plus imaginary I, this is the imaginary I, then beta squared by 2h cut. Okay, then p cap is the momentum operator, which is minus I h cut. So instead there is a derivative d dx of psi naught x equal to 0. Now you take this relation x psi naught x plus beta squared by 2h cut square. Now this I and this minus I is minus I squared, and I squared is minus 1, so minus I squared is plus 1 to h cut into d psi naught by dx equal to 0. So this is, you are getting um, d psi naught by dx equal to, this h cut and h cut cancels out, so minus this beta squared by 2h cut x psi naught x. Uh, sorry, my mistake, there was no h cut square but only h cut on this term, so this h cut actually cancels out, so there is no h cut term left, so you are only left with this kind of a term. Now you can simplify further that this d psi naught by dx is psi naught prime x divided by psi naught x equal to minus beta squared by 2 x. When you take the integral sign on both sides, you have ln psi naught x equal to minus beta squared by 2 into x squared by 2 plus c, the integration constant. So you have minus beta squared x squared by 4 sorry, once again I have to check. Okay, um, okay, so let me correct it from here. So beta squared by 2 psi naught prime x equal to x psi naught x. So from here you can directly write down that psi naught prime x by psi naught x equal to, here I made a mistake, the prefactor will be, there will be a minus sign involved, minus, so minus, then 2 by beta squared x, so then so let me write down here psi naught prime x by psi naught x equal to minus 2 by beta squared into x. So when you take an integral on both sides, you have ln psi naught x equal to, here it will be minus 2 by beta squared into x squared by 2. So this 2 and this 2 cancelling out equal to minus x squared by beta squared plus the integration constant c. So you have psi naught x equal to, this constant term can be adjusted within here, so a e to the power of minus x squared by beta square. So this is your final form, that psi naught x, this wave function will be a e to the power minus x squared by beta square. So this is your final answer of the ground state. So where a is the constant which comes from this integration constant adjusted within the ln and everything. So you choose your answer, that a to the power minus x squared by beta square is answer option A. So this is the correct option. Now question number 5, the correlation function ft is equal to 0 xt x0 0 with xt as a position operator in Heisenberg picture and 0 as ground state of one-dimensional harmonic oscillator will be what? So the correlation function ft is equal to given xt into x0 with 0 state sandwiched in between them, and xt is a position operator in Heisenberg picture. 0 is the ground state of one-dimensional harmonic oscillator. Then what will be the correlation function ft? So here you can write down the correlation function with the position operator. In this case can be broken down into the position creation and annihilation operator format for a harmonic oscillator case, and then applying the Heisenberg picture you can add a time evolution to that, to those operators. So after that you can solve the whole thing, but you have to first break it down into known format of the position operator for harmonic oscillator. So let me write down here at question number 5 is correlation function if t is equal to ground state 0, x t is a position operator at time evolved t, then x at 0, time 0 and then 0. So first of all, because it is a 1D harmonic oscillator problem, so for a 1D harmonic oscillator you can write down your position operator, which is basically position operator without any time evolution. So at t equal to 0 is equal to root over of h cut by 2m omega a cap plus a cap dagger, right? So a cap plus a cap dagger, and then if you have x0 like that, you know that under Heisenberg picture you have an operator's time evolution. Uh, so from there you know that your operator a cap t will be your operator at t0 times e to the power of minus I omega t. So it has a time evolution of the operator, because in Heisenberg picture the state do not, so in Heisenberg picture the rule is that your state does not evolve with times, state, so it is just the opposite of um, Schrodinger picture where state evolves with time but the operator remains fixed. But in Heisenberg picture state does not evolve with time, so but to maintain the equivalence to Schrodinger picture something has to evolve with time. So in this case the operator does evolve with time. Okay, so a cap is a0 to the power minus I omega t and a cap dagger is equal to cap dagger 0 e to the power of plus I omega t. So by this method you have xt can be written down as root over of h cut, sorry, root over of h cut by 2m omega a plus a dagger equal to root over of h cut by 2m omega a0 e to the power of minus I omega t plus a dagger 0 e to the power of plus I omega t, where once you write down that, so you know that what will be your product of xt and x0 is basically h cut by 2m omega. So you have 2 root over h cut by 2m omega, so you can take a square and just take h cut by 2m omega, and then x3 is a0 to the power of minus I omega t plus a dagger 0 to the power of plus I omega t times a0 plus a dagger 0. So there is a product. So from now on I will write a0, actually I'll mean a cap only, and a cap dagger 0 I will only mean a cap dagger, because essentially there is no time evolution when nothing is mentioned, but if there is a time evolution mentioned, then you write as a bracket of t. So I'll follow this notation like this. So here you have h cut by 2m omega. Now you multiply, so you have a cap e to the power of minus I omega t, and the second term is a cap dagger e to the power of minus I omega t, plus you have this term and this term, so a cap dagger a cap a cap e to the power plus I omega t plus a cap dagger e to the power of plus I omega t. So what you have is basically you now can simplify the with only considering the operators, because other rest of the terms are just constant factors which does not matter in the expectation correlation function form. So ft has a form which is sandwiched between two ground states, and so x cap t, x cap 0 and 0. So if you ignore the coefficients with these and only focus on which of these operators which give you which value if you take a sandwich between 0 and 0 state, so that will give you a cap 0, the first term. What it will give you is basically 0, because first of all you have a cap 0, annihilation operator on ground state is equal to 0. Now the second term, what will be 0 a cap dagger 0. So here simply saying a cap dagger is a creation operator, so when it acts on 0 with some prefactor, so which is basically, you know this, I'll write down the form that how it will operate, that a cap when operates on a state n, it will give you root over of n minus 1 kit, but when creation operator operates on n, it will give you root over of n plus 1 kit. So from here you know that a cap, when a cap dagger operates on 0, it will give you 0 plus 1, that means root over of 1. 0 plus 1 kit is 1 kit. So again root over 1 is 1, so you ignore that. A cap root on 1, it acts on 1, so it will give you root over of 1 plus 1, sorry, this is the annihilation operator, so when it operates on 1, so it will give you root over of 1 0. So this is 1 0 and 0 is basically, this is normalized, so this is 1. This is non-zero and giving you the value 1. So the second term is giving you a non-zero value. What about the third term? So this is 0 a cap dagger a cap 0. So here you have a cap dagger 0 is again 0, so this is 0, because this first term is only giving you 0. Now the last term is 0, this term, a dagger, so this is f dagger 0, so this is 0 a cap dagger. So once it operates on creation operator on 0 will give you root over of 0 plus 1, which is 1, and then 1 get. So 1 is constant, so 1 is absorbed here. So then you have 0. Again a dagger operating on 1, that means 1 plus 1 is root over 2 and 2. So you get root over 2, 0, 2 inner product, which is 0 because these are orthogonal, so this will also be 0. So out of these four terms, only you have the second term as non-zero and rest of the other terms are 0. So you have finally h cut by 2m omega, that was a constant free factor anyway, and e to the power I minus I omega t also something this is the constant free factor, and then 0 a cap dagger 0, which is nothing but 1. So this value is 1, that means you are getting h cut by 2m omega e to the power of minus I omega t into 1, which is your final answer, that h cut by 2m omega e to the power of minus I omega t. So your answer is h cut by 2m omega e to the power minus I omega t, which is also the correct answer. So now question number 6 says that Hamiltonian is h cap is equal to h cut omega naught c cap dagger c cap plus half, such that the operator c is defined by the following relation: c square equal to 0 and c cap dagger anti-commutator relation is identity matrix. If the state n is eigenstate of H, then the possible energy eigenvalues for this operator will be what? So here so c cap squared equal to 0 and c dagger anti-commutator is I. So the state n is eigenstate of H cap, then the possible energy eigenvalues of this operator will be what value? So if the state n is the eigenstate of H, okay, so you have to get the eigenvalues of this operator, that means you have to get the energy eigenvalues. Now one thing is very clear, you can directly see from this form itself that this is like a harmonic oscillator sort of an Hamiltonian, because you have n plus half h cut omega naught sort of a Hamiltonian expression. Why I am saying n cap? Because this operator c cap dagger c cap is sort of like the number operator n cap is equal to c cap dagger c cap, where c cap is the creation and c cap dagger is the creation and c cap is the annihilation operator. But you have to check first whether it satisfies or not, whether it is actually that condition or not. For that you have to check whether this c and c dagger are actually the annihilation and creation operators by following these properties. So if these properties are satisfied for those, then you can directly simplify your solution and get to the energy eigenvalue very easily. So let me check that first. So question number 6 is that you have c cap squared equal to 0 and c dagger c or c dagger, whatever is the case, anti-commutator relation is I. That means c dagger plus c dagger c from here, this is I. So and c commutator will be 0, because c times c plus c times c equal to 2c squared equal to 0. Why? because c square equal to 0. So from here you can write, if c square equal to 0 given in your question as a property of C operator, so then C and C commutator bracket will be, anti-commutator bracket will be 0. Okay. And C dagger anti-commutator bracket is I. So for a harmonic oscillator case, you have the creation and annihilation operators like that, and for that case also you know that this kind of a operator formation, operator relation is satisfied. That, so this you can check. How you can check is that, you know, the for harmonic oscillator creation and annihilation operator is given as a cap dagger and a cap. So there you can write down you will know this form, just I use this in the question above, that x cap equal to root over h cut by 2m omega a dagger plus a cap. So just 1 second. So similarly you can write down p cap, the momentum operated by some form of a and a dagger. But basically if you directly want to write down what is the a a and a dagger formation, then you know that it is basically a dagger is equal to 1 by root over of 2m h cut omega um, m omega x cap minus I p cap, and create annihilation operator is 1 by root over of 2m h cut omega m omega x cap plus I p cap. So from this relation, if you want to see what is a dagger, this is basically 1 by 2m h cut omega. Then this product will be has to be taken, so m omega x plus ip and then m omega x minus ip, which is 1 by 2m h cut omega, then m omega square x squared minus I m omega xp plus I m omega px minus I squared is plus 1, so plus p squared. So you have 1 by 2m h cut omega m squared omega squared x cap squared plus p squared plus I m omega, in fact minus I m omega xp minus px is basically a commutator bracket of x and p. So you have 1 by 2m h cut omega p squared plus m squared omega squared cap squared I x and p commutator bracket is basically plus I h cut. So plus I h cut multiply with this, so minus I squared is plus 1, so plus 1 m omega h cut. Similarly, if you derive what is your a cap dagger a cap, then you will get 2m h cut omega. Just the order of these terms you are taking will be different. So then you have m omega x cap minus I p cap m omega x cap plus I p cap, which is basically will give you 2m h cut omega m squared omega squared x squared plus um, p squared. But instead this order will be different, right? Because you have now first um, plus im omega xp minus im omega px. So the order of the operators here will be different. So the only difference it will make is that 1 by 2m h squared omega p squared plus m squared omega squared squared plus you have a plus sign with x and p, a commutator bracket, which is plus h cut. So plus h cut multiplied with plus I will give you I squared, which is minus 1. So this is minus 1 m omega h cut. This is your thing. So once you have that, you see that if you take a commutator bracket, anti-commutator bracket relation of a and a dagger, which is nothing but your a dagger plus a dagger a. So you have separately derived these two terms for the creation and annihilation operator of a harmonic oscillator case. So now you directly write down those forms. So sum up those forms. So 1 by 2m each card omega. Now this term plus this term. So m omega each card has opposite sign. So that will get cancelled out. Only you have 2 times p squared plus m squared omega squared x squared. So this is cancelling out. So you are getting so in this case you see that this is not equal to identity matrix, but only because here they are like the operators given. Just one second. So as I was telling you that harmonic oscillator case, these are not satisfying this anti-commutator relation, because if you see that they will satisfy a dagger equal to I kind of a relation, because in that case you will have this p square and m omega square terms cancelling out, and only 2m omega by h cut by 2 will give you by 2m omega h cut will give you I. So this is showing that the normal creation annihilation operator you know from harmonic oscillator case is are bosonic operators. So bosonic operators for a dagger of a harmonic oscillator case. So they satisfy commutation relation, not anti-commutator relation. So they satisfy commutator relation. Like for them, we will have a dagger equal to I, and a commutator equal to 0, and a dagger commutator equal to 0. But for this case in this question, you cannot do that, because these are fermionic operators. So see, the C operators are fermionic operators, and the rule is that fermionic operators satisfy anti-commutator relation, which are given as in the question. Anti-commutator relation. That means C is equal to 0, anti-commutator bracket, C dagger anti-commutator bracket will be 0, and out of apart from these properties, another property is C dagger C equal to I for the anti-commutator bracket. Now you can define the number operator also for from this anti-commutator from these fermionic operators. So number operator actually means that how many number of particles can remain in a state. So number operator in a harmonic oscillator case, you knew that here the number operator used to be simply a dagger a. In this case also, for fermionic operators, your number operator is actually C dagger C, right? So the Hamiltonian form that is given to you is not exactly the harmonic oscillator problem. but it is somewhat similar to that, but instead of bosonic operators, now you have Fermionic operators. So you have C dagger C plus half. Okay, so this you can replace by H cut omega naught, n cap plus half, and n cap is your number operator. Now, because you cannot state that this is directly the harmonic oscillator case, so you can formally represent like this a state, let's say a number basis state n is a linear combination of two states 0 and 1, let's say. So this is, so what was in the question is that you had to know what is the eigenvalues for n equal to 0 and n equal to 1, what are the eigenvalues, right? So if these are the two eigenbases, then you can write down your actual state as a linear combination of both, right? So so let's say psi kth state can be written down as a0, sorry, this can be written down as so this is a linear combination of this out of these basis states 0 and 1, and an and bn are the coefficients to that. Now when you deal with only this state n equal to 0, then at psi equal to 0, that is when you are at n equal to 0 state, then you have a0 equal to 1, because the whole state is actually only 0 and no component of no linear combination of one state should be there, and b0 equal to 0. In this case your Hamiltonian given by this form h cut n plus half h cut omega naught is basically h cap acting on psi is equal to h cut omega naught n plus half 0 plus bn 1. So you have h cut omega naught common, then n cap operating on an 0 will give you an. N cap is the number operator operating on the state 0, so this will give you the value okay. I think there is a confusion. Okay, so here you break down into two parts. So n operating on this whole thing will give you this, where I am writing n0 as the number for the 0 state, and n1 is the number operator eigenvalue for this one state, plus half times this whole state linear combination is against psi, right? So then you know that for 0th state the number operator eigenvalue will be 0, so this term is actually 0, and you are only left with bn, and this n1 will be 1, because so n0 and the eigenstate we also have to write down as 0, and this also have to write down as 1. Why? Because the number operator acting on 0 is actually 0 times 0, which is 0, and the number operator on the state 1 is 1 times 1, which is actually 1. So this is what we are getting. So this term goes to 0 and this term is actually 1. So this is h cut omega naught bn, this is 0 in so this term you ignore, and bn into n, plus the other term is half h cut omega naught n 0 plus bn 1, right? Now if this is the case, then you have roughly half h cut omega naught an 0 plus bn h cut omega naught plus 1, uh, sorry, h cut omega naught plus half 1. Now when you are at a state n equal to 0 equal to psi, then you have h cap 0 is equal to half h cut omega naught an 0 plus bn h cut omega naught plus half 1. Now because on the left hand side you have only 0, so for the eigen, if it is an eigenvalue equation with the eigen state and eigen value, then the eigen state must be 0 only and no other state should be present. That means this whole term should be cancelling out, or bn should be going to 0, and you will be having half h cut omega naught, and for n equal to 0 it is a0. So here bn equal to b0 equal to 0 and an equal to a0 non-zero. And also from the state you got that psi is equal to an0 plus bn1. So if psi state is itself 0, then it is 0 plus b01. So because there is no state on the left hand side with 1, so this b0 terms has to goes to 0, as you can see, and a0 term has to go to 1 because this is just 0. So just combine the both sides, it is a0 equal to 1 and b0 equal to 0. So from here you say that a0 not equal to 0 and equal to 1. So from finally you get from the Hamiltonian eigenvalue equation is that h cap 0 is equal to half h cut omega naught into 1 0, which is basically h cut omega naught by 2 0. So eigenvalue for the state n equal to 0 is half h cut omega naught. Now for n equal to 1, your psi state is basically 1, which is like a1 0 plus b1 1, but on the left hand side there is nothing in 0, so a1 equal to 0 and b1 equal to 1. Now writing down the Hamiltonian, h cap 1 is equal to half h cut omega naught a1 0, so half h cut omega naught a1 0 plus b1 h cut omega naught plus half b1 h cut omega naught plus half 1. Now because it is an eigenvalue equation and a1 is also already 0, we saw from the state, so this is 0 plus b1 half plus, so this is not just okay, so half h cut omega naught, and so if you take b naught common, so actually it is 1 plus half, actually h cut omega naught comes common outside, so this is 3 by 2 h cut omega naught. So this is, so this term is this h cut omega naught plus half h cut omega naught, so this is 3 by 2 h cut omega naught, and this term was going to 0 earlier, so this is, so this is basically b1 times 3 by 2 h cut omega naught 1, and you saw b1 is 1, so this is just h cap 1 equal to 3 by 2 h cut omega naught 1. So you get to see that the eigenvalue is, your energy eigenvalue is 3 by 2 h cut omega naught for the state n equal to 1, and you got from earlier that half h cut omega naught for the state n equal to 0. So these are the eigenvalues that are asked in the question. So your eigenvalues are this and this. Now question number 7. Recall the definition of the spherical harmonics ylm in like that, and n is a unit vector with the orientation theta and phi. If 1 minus 1 y is equal to this, then y10 equal to this, where a equal to what you have to identify. Now here you have to deal with the angular momentum operators, because the eigenfunction is here, the ylm is the eigenfunction of the angular momentum operators L square, Lz, etc. And so this will be helpful, and also the ladder operator will be come to use, because ladder operator operating on this will like step up or down on the state ylm. And because you can see these two states, this is L equal to 1 fixed for both of them, and 1 for one m equal to -1, and the other one m equal to 0. So these two are there. So as if on the m you are stepping up and down from 0, you are going down to -1, so like that. So they are related by angular momentum ladder operators, and that is what will help us in this situation. So basically what you do is that question number 7 is that you have L plus y1 minus 1 is equal to y1 0. Okay, so L plus minus are the ladder operator in angular momentum. So you know that the formula is L plus minus, if you have the state as ylm, that is equal to some coefficient depending on L and m, which is aml, yl, m plus minus 1. So this is basically the coefficient value is a root over L into L plus 1 minus m into m plus minus 1 times h cut outside the root, and yl m plus minus 1. So L plus operator changes ylm to yl m plus 1 with some prefactor, and L minus changes ylm to yl m minus 1 with some prefactor. So this is the definition. Now you know that if this is the definition, then L plus acting on y1 minus 1 will give you y10 with some coefficient factor, right? So what will be this factor? So this AML factor is root over of L, so L equal to here 1. So for this case, L equal to 1 and M equal to -1. So this is root over L into L plus 1 or 1 into 1 plus 1 minus M into M plus 1 is -1 minus 1 plus 1. So this part is already 0, each cut y10. So you have only root over of 2 each cut y10. Now you can represent this L plus in terms of, because you have been in the question, you have been given the form of y11 in terms of theta and phi. So you have to change into theta phi representation of the angular representation of the operator L also, L plus also. So L plus y1 minus 1. So L plus in operator form in theta phi format is h cut e to the power of I phi del theta, plus this you can take this you can note from the like textbook or the lecture notes, that this kind of a relation is valid. So this is I cot theta del phi. Now the expression of y1 minus 1 is given in the question. So this is root over 3 by 8 pi e to the power of minus I phi sin theta. So that then this is h cut e to the power of plus I phi root over of 3 by 8 pi, then into, you take the first derivative e to the power minus I phi cos theta plus so theta is only in the sin theta form, then on the del phi part you have I cot theta sin theta minus I e to the power of minus I phi. So this is h cut e to the power I phi root over 3 by 8 pi. Now this e to the power minus I phi, take this as common. So this is cos theta plus cot theta is caused by sine. So this is I sine theta, and this is I squared minus I square in fact. So this is minus I square is plus 1. So this is sine theta. Yeah, this is cos theta again, because cot theta is caused by sine. So what you get is this and this cancelling out. So you have h cut root over 3 by 8 pi into 2 cos theta. So y 1 0, which is basically your L plus acting on y1 minus 1. Okay, so this is giving you this is giving you this, which is nothing but your root over of 2 y 1 0. Why so? Because you saw that y lm or y1 minus 1 is root over 2 y1 0, and just now directly operating L plus in theta phi format on y1 1, you are getting this. So when you equate these two like this, so you get y1 0 is equal to root over 3 uh, by 8 pi h cut 2 cos theta divided by root over 2, or you get h cut root over 3 by 8 pi root over 2 cos theta. So from here, if you compare with your expression given in the question of y10, you will see that a, which is this root over a, was present there. So instead of root over a, this is root over 2, so equal to 2 in our case. So the answer is a equal to 2. So our answer is this root over a is actually root over 2, so equal to 2 is the answer. Now question 8 is the x component of the electron spin measurement gives plus half h cut. On this resulting state, which we call psi t naught, we apply the Hamiltonian as this, where v is the magnitude, z is the electron spin, then the state psi t will be what? So so in this case, you have to apply you have to take the main state psi t naught, and then you have to operate on it the time evolution operator, UCAB operator, so that you get a state at a later time, which is psi t. So what we will do is basically, let us write down um, this is question number 8. Now the first form is that because the spin measurement or the measurement on the system had spin equal to plus h cut by 2, then you can consider the state at initial time or state at psi 0 as a state with a triplet kind of a state, which is 1 by root over 2 spin up plus spin down, because you are getting plus h cut by 2. If you had got minus h cut by 2, then there will be a minus sign here, but for plus h cut by 2, this is the standard state that on the basis of like sx basis, because in the question it is given that your sx operator is giving the h cut by 2. Yeah, the x component of the electron spin is giving the value h cut by 2, and sz is a z component of the spin. So you know that sz forms actually your standard basis for this spin operator. So sz eigenfunctions acts like a basis. This is spin up and spin down. These are the basis vectors, and measurement of sx give an eigenvalue of h cut by 2. That means your state will be a linear combination of these basis vectors with a plus sign, which is a triplet kind of state, which is this state, right? So this, you can identify this as a state plus subscript x, means this has been measured with respect to the spin operator sx cap. So this is the state for the measurement of Sx cap operator. So this is 1 by root over 2 up plus down. Now once you have this, you know that your any state psi t under the time evolution operator can be written down as ut comma t naught psi t naught, where u is the time evolution operator, which has a specific form that e to the power minus I h cap t minus t naught by h cut psi t naught. So this is h is a Hamiltonian operator, t minus t naught is the change in time. This is a standard form of the time evolution operator. Now you know the Hamiltonian form that is given in the question, that is minus I eb by h cut mc, then sz, this is the Hamiltonian, then t minus t naught, and this h cut comes from there. So h Hamiltonian is basically eb by mc is z cap. So this is the form, and then psi t naught. Now you redefine your this whole thing as e to the power of minus I omega sz t minus t naught psi t naught, where omega is equal to eb by h cut mc. That means on a state, this kind of an time evolution operator will operate to get it to a later state t. Now similarly, when you have the initial state as 1 by root over 2 up, which is basically on the sz basis, so I am writing subscript z. So when you have a state like this, okay, so then on each of this term you will have a time evolution operator operating. So 1 by root over 2 e to the power of minus I omega sz t minus t naught z plus e to the power of minus I omega sz t minus t naught down. So from here you can say that this up state is the eigenstate of sz only with the eigenvalue of plus half. Okay, so basically sz operator acting on this state, this is the eigenstate of this, so this is plus half on again this state back, but when sz operator operates on the other state, which is also an eigenstate but with an eigenvalue of minus half. So when this Az operator in the power operates like that, so you have minus I omega into plus half t minus t naught, again up state, plus e to the power of minus I omega. This is Az operator giving minus half because you have down state, so this is t minus t naught down z. So this is 1 by root over 2 e to the power of minus I omega t minus t naught by 2 up state plus e to the power of plus I omega t minus t naught by 2 down state. So here you can redefine your omega by 2 as omega, because this is just a constant term, you can redefine any term. So you redefine like that. This is just for our answer has to be matched with the options given to us, so that is why this is needed. Otherwise this is also correct what we have right now done. So you can say this is omega prime, which you can equivalently write as omega. Okay, so now omega definition is eb by 2 mc h cut. Earlier we defined it is just eb by mc h cut, but now there is a half factor also. So this is this thing plus e to the power of plus I omega t minus t naught down state. So this is your final answer of the state. So the answer is option number D. First term there is a minus sign, and the second term there is a plus sign. Now question number 9 is d alpha is equal to e to the power of alpha alpha dagger minus alpha star alpha a is the displacement operator, where a and a dagger are the lowering and the raising operator. Then the quantity d dagger alpha a dagger d alpha will be what? So this is something that is related to the displacement operator, and for the displacement operator, when you see such kind of a thing, you directly use the theorem or the result of Hausdorff result for displacement operator is that there is this direct formula that d cap alpha a d cap alpha is equal to so this is equal to a plus alpha. So then if you take this whole thing dagger on both sides, this is plus not dagger, this is a cap plus alpha whole dagger, then you know that ABC whole dagger is C dagger A dagger C dagger B dagger A dagger. So then by that you write down so this is similar to this on the left hand side, and the right hand side is just A dagger plus alpha star. So your answer is D. So directly use this result and you will take a dagger and then you end up with this. Now the final question, question number 10 is that one dimensional simple harmonic oscillator using the number basis construct a linear combination of 0 and 1 such that x cap is as large as possible. So um, x cap is as large as possible, that is what you have been asked about. So first you can express x cap in terms of the number basis vectors, right? And maybe from there you can get to the solution. So basically how you can implement the number basis vectors in this case, x cap is as large as possible, but this is x cap expectation value, that you also have to note. So let us write down first that it is a harmonic oscillator kind of a problem, right? Now so x cap expectation value will be having a particular form, because x cap have a particular form in terms of raising and lowering operators, which is h cut by 2m omega square root, then psi a dagger plus a psi, right? So this psi state is basically can be written down as a linear combination of these two basis states C0 0 plus C1 1, because these are the two standard basis states you have been given, so that any state will be a linear combination of that. Now for psi to be normalized, which is has to be for being a physical state, the condition on these coefficients is that C0 whole mod squared plus C1 whole mod square equal to 1, right? So then you have um, root over of h cut by 2m omega C0 star 0 plus C1 star 1, this is in the bra form for this part, and then a dagger plus a, then operating on C0 0 plus C1 1. So this is root over of h cut by 2m omega C0 star 0 plus C1 star 1. A dagger acting on this will give you, so a dagger is a creation operator, so it is, as I said earlier, that a dagger will be root over n plus 1 into n plus 1 kit, and a will be root over n into n minus 1 kit. So for a dagger, when operates on this 0 state, it will be root over 0 plus 1 is 1 into 1 kit plus C1. A dagger on this 1 kit is root over 1 plus 1 2 to 2 kit plus a on C0 is 0 because that is a ground state, plus a on C1 is a1 root over of 1 0 kit. So you have root over h cut by 2m omega c naught star 0 plus c1 star 1 c naught 1 plus c1 root over 2 2 plus c1 0, which is root over of h cut by 2m omega. So when you take this with this is orthogonal, so this will give you 0. Only this with the 0 state will give you non-zero. So you get c naught star c1 0 0, which is 1 because it is normalized. Again with 1 you only get non-zero with 1, so c1 star c naught 1 1. Rest of the terms are only 0, so you get root over of h cut by 2m omega c naught star c1 plus c1 star c naught. Now how we can simplify this even further, that you already got under normalization condition that c1 whole mod square plus c1 whole mod square equal to 1. So c naught can be written down as root over of 1 minus c1 whole mod square. Okay, so then c naught star c1, because expectation value x cannot be complex, so it has to be real, right, because it is an expectation value. So in c naught star, basically you need to mean the modulus of each of these terms. So basically that means c naught modulus c1 modulus, which is basically c naught c1 modulus can be written down as root over of 1 minus c naught square from this relation. Similarly, c1 star c naught is basically c1 modulus c naught modulus, which is again c naught root over of 1 minus c naught mod square. So this is equal to root over of, this is 2 times, so this is root over of h cut by 2m omega 2 times c naught c1, which is 2 root over of h cut by 2m omega c naught root over of 1 minus c naught squared. So this is what you get. Now once you obtain this, you can see when x cap will be maximum is when dx cap, so only variable here is c naught, so you have to take derivative with respect to c naught when it is 0 for to be maximum. So by taking the derivative you ignore these constant terms, only focus on c naught. So c naught, first of all this is on the first term plus mod c naught 1 by 2 root over 1 minus c naught whole mod square into minus 2 c naught equal to 0. This 2 and this 2 cancels out, so this is root over of 1 minus c naught minus c naught whole mod square 1 minus root over c naught whole mod square equal to 0. So you know, take it up, so this is 1 minus c naught whole mod square minus c naught whole mod square divided by root over 1 minus c naught whole mod square equal to 0. So you get 1 minus 2 c naught whole mod square equal to 0, or c naught whole mod square equal to half, or c naught equal to 1 by root over 2. So you get c naught equal to 1 by root over 2, and then c1 equal to 1 minus c naught whole mod square, which is again root over of half, which is 1 by root over 2. So for x to be x expectation value to be maximum, these two are the values to be satisfied. So then the state becomes linear combination of both of them, which is c naught times 0 plus c1 times 1, which is basically nothing but 1 by root over 2 0 plus 1. So you get your maximum expectation value of x cap as root over of h cut by 2m omega. So what was that? Root over h cut by 2 omega into 2 into c naught c1. So this into 2 into c naught whole mod is 1 by root over 2, c1 whole mod is 1 by root over 2. So this and this cancelling out. So you are only getting root over of h cut by 2m omega as the maximum expectation value answer. So your answer for this question will be, let me check. Okay, so you are asked that for x cap expectation value to be maximum, what is the state? So that is that we have obtained 1 by root over 2, 0 plus 1. So B is the correct answer. So with this, we solve all of these questions of this week.